Welcome, everybody. So many of you are probably in this room because you're facing some of the challenges that come with safely integrating and securing AI at your company. But there's few products out there that have really had to deal with these challenges at the scale and the scrutiny of Claude. So today, you're going to get this rare behind-the-scenes take on Claude. You're going to also hear about some of the new capabilities in Bigtable that are coming up that are going to help it evolve for this new agentic era. So I'm Chris. I'll be chiming in here as we go along to give some additional details on many of these Bigtable features that Anthropic found along their Bigtable journey. And you'll hear more from Shaoyi later on what they really faced along the way and what things they had to solve. But this is really the Anthropic story, so I'm going to hand off to Akshay here and just let him jump into essentially what they were looking for as they were looking for a database for Claude.
Thanks, Chris. Good morning, everybody. My name's Akshay, and today I'm here with Shaoyi from my team here at Anthropic. Today, we're going to be talking to you a little bit more about how we built the data infrastructure behind the constitutional AI that is Claude, powered by Bigtable, which stores every Claude interaction with purpose-built security and with retention at massive scales. I'll talk to you a little bit more about the context and what we're trying to do, as well as the architecture, and then I'll hand it off to Shaoyi to talk a little bit more about challenges before going back to Chris, as we mentioned, who'll talk a little bit more about how Bigtable is evolving for the Gen AI era. For those of you who don't know us, Anthropic is an AI safety company. Our flagship product is Claude, a frontier large language model family that powers consumer products, a developer API, and as well as Claude Code for software engineering tasks. Every one of these relies on Bigtable. Let me kick it off by kind of motivating you with some of these metrics that we've pulled from Bigtable a couple of weeks ago. These are probably out of date at this point, but it should give you a rough sense of the ideas of the scale that we're kind of dealing with here. As I mentioned, every prompt, every completion, and every conversation with Claude, along with associated metadata that we're allowed to store, goes through this system. Let's talk a little bit about why this is hard. When you're talking to a large language model, these interactions are uniquely sensitive. Me, I share my personal financial information with Claude, as well as personal health information as well. Other people share their business secrets, or may even be sharing company confidential IP as well. We need to protect that data from external threats, as well as internal misuse. But we also need to balance that with the need to retain it for legitimate purposes. Our mission, to fulfill our mission to build reliable, interpretable, and steerable AI systems that serve humanity's best long-term interests, rely on us being able to store a subsection of these conversations. As you can tell, these requirements pull in vastly opposite directions. Now, this led us to a set of requirements that don't really fit neatly into any off-the-shelf solution. We needed cryptographic access controls, not just access control lists. We needed automatic retention that cannot be bypassed by application bugs. We needed high write throughput for real-time inference needs. And all of this had to be done at a cost-efficient petabyte scale, multi-petabyte scale, I should say.
And so this is when we introduced the Anthropic team to Bigtable. This is Google's powerhouse NoSQL database. You may have seen in Sundar's next blog, he highlighted how Bigtable has actually been used for years within Google for some of our own largest services, whether that's ad serving or YouTube recommendations. But it moved to a cloud service about 10 years ago, and some of the largest applications on the internet now run on Bigtable. So just this week, if you've been around Next, you may have heard some other Bigtable stories from Snap, Spotify, Palo Alto, and Etsy. But what makes Bigtable Bigtable? First, it is that speed at scale. And that is for both reads and writes. These mixed workloads don't really compromise. You can get a lot of performance out of both on Bigtable. And then the core here that was being alluded to earlier is just its flexibility. That's flexibility of the data model itself. So as you're changing your application, your database can automatically adjust to that. But also flexibility of deployments. So you have a lot of freedom in where you're going to put your various Bigtable deployments. You could have a cluster with thousands of nodes running in the US, Then one day you decide you're going to enter the EU market. And then you can, with a few clicks of a button in the console, spin up another cluster in the EU, have that all automatically replicated, and that can have a completely different scaling policy because that's a new market. You might just need to start growing there. There's also a lot of new built-in features for real-time intelligence, whether that is things like write-on aggregation. So you want to start counting your likes or your clicks or wallet transactions. You can do that, these write-on aggregations. But there's also this concept of a continuous materialized view, where you can have streams of data coming in, and then each row gets transformed into a basically ready-to-serve copy of data for your application. And we really try to meet developers where they are. Bigtable does have an API that's available in about 8 different languages, but there's also a SQL interface for it. There's also a API compatibility with Cassandra, HBase. New this week is also Aerospike. Or if you're in Claude or some vibe coding tool, we also now support MCP. So with that, what was your take? Why did you guys, what did you guys see in Bigtable for you?
When we dug a little bit more into Bigtable, we realized that it would be an excellent solution for us. There's a whole bunch of features around Bigtable that make it uniquely powerful. Firstly, cell-level timestamps are an incredibly powerful feature once you're able to harness the power that they offer. Each cell can have its own time to live, which is perfect for the key expiration model that I'll be talking to you about in a bit. Secondly, Bigtable offers us massive scale without breaking a sweat. As Chris mentioned, scaling up is as easy as clicking a few buttons. Scaling down is just as easy as well. But when you tie together the autoscaler that Bigtable offers, you reduce the manual toil of doing that scaling automatically. For us, where we have a fairly diurnal pattern in our workload, this means tangible cost savings. Third, row-level consistency. Bigtable is able to offer row-level consistency across a single row, so it gives us the atomic operations that are necessary for us to do the key management that I'll talk about. And fourth, we saw the direction that Bigtable was heading in, and we could see the growth in feature set. And the growth and the ability to develop on top of this large-scale product was something that really resonated well for us. Let me tell you a little bit more about what Bigtable does for us so we don't have to do it ourselves. When you're using a managed service like Bigtable, you expect the management to just be seamless. And that's exactly what we found. So Bigtable stores contiguous rows of data on tablets. As data volume changes and rows expire, Bigtable automatically handles the splitting of these tablets and merging of these tablets to provide for optimal performance. Bigtable also provides built-in replication at the click of a button. For us, when we needed to scale across multiple zones in a particular region, all we had to do was 5 button clicks. And there it was. Our cluster was ready. Third, scaling up and scaling down did not require any application downtime. We did not have to set up a second replica to handle our reads and writes before being able to do any kind of scaling operations. Zero disruption for us. Fourth, automatic compaction. For us, at petabyte scale, every little bit of cost matters. Bigtable automatically handles compaction for us, and all these expired cells that I'll talk to you about with these cell-level timestamps, they just disappear automatically. Finally, we also get a bunch of separation between compute and storage. So we know that the nodes, even if there's an unhealthy node in there, Bigtable is just going to take care of that for us. We don't have to worry about node health. We don't need to worry about the health of the service as a whole, because we know that once you have the second replica, the health management service that Bigtable provides under the hood for us will just take care of handling request routing for us to a healthy instance. All of these features mean that a lean team like ours could deliver this petabyte scale system efficiently and effortlessly. Let me take you through a little bit more about the architecture on the system we've built on top of Bigtable. Here's a high-level overview of what we've built to ingest data into Bigtable. Claude's inference team writes prompt and completion pairs through our ingestion service. There, we compress the content with zstandard and then encrypt it with a unique key per item. That's right. For the tens of billions of rows we have, each of those records has a unique key. And then we write that right back down to Bigtable. We handle access for different use cases with keys that are stored alongside the content, each with their own expiration. Our workload really involves two main tables on Bigtable. One, the data table that stores most of all of the content, as well as the individual row-level keys. Now, you can see that I also have a little bit more about the timestamps that we're using. So for instance, for the content, we're using the current timestamp when we write it to Bigtable. But for the keys, we'll actually future date those keys to expire for how long we're allowed to retain that data. Second, we also have a keys table, and that stores the rotating encryption keys that change daily. These rotating encryption keys are what actually encrypt the keys that we store in Bigtable, because otherwise, if you could just store the key in Bigtable unencrypted, then a threat actor who has access could just decrypt the content. I'll talk a little bit more about how we manage our encryption in a minute, but the key thing to note here is that we have two different tables with two different properties that we need. One, extremely high write volumes, and two, write volume where we have once per day writes, but read thousands of times a day. And Bigtable just scales effortlessly across both. Let me talk to you a little bit more about the row keys that we use in that data table. Bigtable thrives as a key value store, and choosing your row key correctly can unlock a lot of the performance potential that Bigtable has to offer. In our data table, we had to pay special attention to our row key design. It may seem trivial, but it can make or break your performance on Bigtable. For us, a lot of our content IDs start with common prefixes like what I have here. Instead, for us, we know that the highly entropic part of the row key is actually at the end. So all we do is just reverse the key, and that way we get a good distribution across all of our row keys. Shaoyi will talk a little bit later about exactly why this matters when we talk about the challenges. Now, going back to the encryption key piece for a little bit, this is our encryption hierarchy, right? You might be a little bit surprised when I said that we actually store the keys alongside the content, and you must be wondering, look, if the keys are right there, isn't that the crown jewel? Well, it turns out that we don't actually store the content key alongside the row. What we do is we actually derive another key, and specifically multiple keys, based on each business purpose that we have to access that content. Those re-encrypted keys are what we store alongside. Now, you might say, but Akshay, like you have some defined key derivation function. Couldn't you just get the keys to the kingdom by just re-deriving that function? You're right. So that's where we come in with the daily encryption keys, which encrypt those keys. Now you might be wondering, but Akshay, you just have keys in two tables. Now you've made that one read turn into two reads. Now what? You're right. And to that, what we do is we actually root our trust in a cloud KMS. So those daily encryption keys that we have that get rotated, we don't actually just store the plain key material, though that's actually encrypted ciphertext where the root key is actually rooted in a cloud HSM. Now, this solves that chicken and egg problem that we have, because ultimately, if we can't rely on KMS, well, there's a lot of banks and financial institutions that do rely on it, so we have a bit of a problem. So for us, KMS ends up being quite all right. Now, all of this encryption and decryption sounds pretty expensive, right? But it turns out that modern CPUs actually accelerate these workloads pretty quickly, so the overhead here is actually quite negligible. I talked a little bit about this purpose-based access control thing earlier. Now, this key and encryption model actually allows us to do a lot of very powerful internal attribution on who is accessing which customer's data, and specifically which rows of that customer's data. Now, instead of traditional role-based access control, we actually do purpose-based access control. When we look at serving a particular piece of content out of our serving layer in front of Bigtable, we don't just ask, who are you? But we also ask, what are you trying to do and why? This is because our terms of service actually prohibits us from using a lot of our customer data for different business purposes, and we don't want to leak that across different departments. A trust and safety reviewer would necessarily be using a different key than a researcher with different expiration times for the same data. This is the key part that allows us to provide differentiated access for different business purposes. And this is where Bigtable cell timestamps become incredibly powerful. Each access key is a cell with its timestamp set to its expiration. When Bigtable runs its garbage collection, expired cells are automatically removed. This means no key, no decryption. The revocation of access happens all the way down to the storage layer, with very minimal and easily auditable application logic needed to enforce this constraint. What I mean by that is that garbage collection in Bigtable is asynchronous. So we do make sure that all reads apply this timestamp range filter to exclude cells that are expired, but not yet garbage collected. On our services read side, auditing is straightforward. Simply emit an audit log anytime there's a decryption operation. This makes it extremely easy for code reviews to happen without introducing new security vulnerabilities that might introduce unaudited access to user data. This simple invariant enables us to move fast while keeping user data secure. Now, I've talked a lot about how we store data, but here's a timeline view for those more graphically inclined. As I said, Bigtable offers differentiated retention policies for different column families. When we write content, we don't know ahead of time when it might expire, as async processes that run after we serve the response might either extend retention or reduce retention. For instance, if there's an issue with Claude, a customer might write in a support ticket, we might ask them for consent to access their data, and that might actually extend the retention for how long we're allowed to look at that data. To that effect, when we write the content, we actually don't expire that content on its own. We do not set a garbage collection policy on the content. However, as the different keys expire at different times, so like let's say 30 days for trust and safety, 45 days for analytics, 60 days for customer service, what have you, the key thing to note here is that once that last key expires, because we don't write the per row content key anywhere, when that last key expires, all of the content becomes permanently undecryptable. In effect, it's just gone. And this is the main insight here. We want to push the security guarantees of our system as deep as they can go. In this case, this is the storage layer. Instead of trusting ourselves with writing good, perfect application layer code, we want to make it mathematically impossible to access the data without the right key at the right time. Seems great, right? Sunshine, rainbows. The whole project went off without a hitch, right, Shaoyi?
Yeah. Hi, I'm Shaoyi. Akshay and Chris just described Bigtable as a magic wand, but let's also talk about what was harder than we thought when we operate at the scale. So the first challenge is row key hotspotting. Bigtable stores data sorted by row key and split into tablet servers. You can think the tablet servers as horizontal partitions, each living on a different server. If your row keys cluster together, all writes hit the same tablet while the others are sitting idle. On the hood, Bigtable automatically split the sorted data into smaller tablets as the data grows. It's great at detecting hot tablet servers and splitting them further. But when all your keys starts with the shared prefix that Akshay described earlier, they all land on the same key range. And no amount of splitting could fix this shared prefix. You'll need diversity at the front of your keys. Our fix was simple. We just reversed the content ID. This works because our content has high entropy towards the end. Reversing it puts the randomness at the start of the keys, which is exactly where Bigtable needs this. Since we mostly do point lookups instead of range scans, this costs us nothing. However, you might also be thinking there's a natural alternative, hash prefix. It works great too. This gives you guaranteed uniform distribution across the key space, regardless of the underlying ID patterns. Bigtable is excellent at automatically splitting those prefixes. And here's a critical lesson. You want to make this choice early. Migrating row keys across petabytes of long-lived data is a project that you really don't want to take on. Now, moving on to the second one, large values. Bigtable has practical size limits for cells, With Claude handling multi-model inputs, images, documents, longer and longer context windows, we regularly need to store blobs way beyond those limits. So we build a blob storage layer. Small blobs under 4 megabytes will go inline with the parent row. Larger blobs are first split into 4 megabyte chunks, each independently compressed and encrypted, stored in a separate table. Then the parent row only holds the metadata, kind of like a pointer to the separate blob table. However, before you build something like this, you might want to ask yourself, do you actually need single-digit millisecond retrieval for those large values? In many systems, the answer is no. If you can tolerate slightly higher latency, it's perfectly reasonable to store a pointer to the Google Cloud storage in your Bigtable and retrieve the object on demand. It's much simpler to build and operate. We needed inline storage for our specific latency requirements, but the GCA's pointer approach is generally the right choice for many other use cases. The third challenge is large-scale migrations. Any production system that lives long enough will accumulate schema drift. We do all kinds of stuff. However, at our scale, mutation is never the hard part. Those are cheap, single-row operations. The hard part is finding the rows that we need to operate on. This is where Bigtable's data model gets very honest with you. It's optimized for key value access. Give me a row key, I'll hand you a row. There's no update some rows where the condition is X. No secondary index, and if your condition isn't encoded in the row key itself, the only way to find the matching rows is to scan the entire key space, evaluating the conditions row by row, issuing mutations one at a time. In a relational database, that's just an index lookup. Here, at roughly 200 petabytes, a naive full table scan could take weeks or months of compute. And it's hitting the same cluster that's serving production traffic. So what we actually really need is a scanning infrastructure that's systematic, restartable if the worker dies, and also be gentle on the production. And it turns out that's exactly the same infra we need for one of our most frequent operations, which is deleting the rows when all the access keys have expired. So let me show you how that works in practice. So for row cleanup, Akshay mentioned that we have cell timestamps for access control. Each key in the key column family got a future dated timestamp, set to expire exactly when our terms of service says that purpose for accessing this row expires. The Bigtable garbage collection automatically removes those cells when they expire. However, in Bigtable, there's no way for us to say, delete this entire row when this column family is empty. So when all the access keys has expired, the raw content still sits there. The content is permanently undecryptable, but we are still paying storage cost. Across tens of billions of rows, that's a lot of wasted storage. And Chris will talk about how we do make row cleanup easier with Bigtable SQL.
So this challenge that is being described about key value stores and missing some of that query functionality, this is exactly why we introduced Bigtable SQL a couple years back. So Bigtable SQL, it's using the exact same Google SQL dialect that you're going to find across Spanner and BigQuery. And what this does is it's going to give you a lot of expanded functionality. So it's not on you as the application developer to now pull down a bunch of keys and manipulate that in your application layer, worry about scalability and all that. You can take advantage of a lot of those SQL functions that are available, whether it's something simple, like I just have to go parse this string, or you have to do something more sophisticated, like I have a bunch of vectors and I want to go do a KNN search. That can just be pushed back to Bigtable now. And so that's standard SQL. We have that. But we've also extended this SQL dialect for a lot of functionality that actually makes it interact well with the NoSQL model. What does that actually mean, though? Let me just give you a quick example. There's lots of these, so I won't get into all of them. But just as a quick example, when Akshay was talking about the timestamps, this SQL statement, which you're going to see, when you see that with history is true, that's going to give you access to everything in that timestamped history. That also can be a point-in-time lookup, like give me all the values between this time and that time. And then you'll get back bundles of all these cell values. But oftentimes, then you want to do some kind of forecast or analytics on top of that. And so there's functions like onpack that'll take that nested Bigtable model, flatten it in that more traditional one timestamp per row model that you're probably accustomed to working with in analytics. And so again, there's a lot of these. I won't, but that was just one example of how we extended the language. So now in GA, you can also build continuous materialized views using that same dynamic SQL language. A continuous materialized view, that's going to incrementally update each row of data as it comes in. Shaoyi mentioned earlier about having to do these large table scans. These do not operate that way. These are, every time you get a row of data in, you will incrementally update a second result set. These automatically scale globally. You're going to have an eventually consistent copy of your view. So users in Europe are going to be looking at the same data that's going to be in the US. And it's all fully managed. It's integrated into the Bigtable environment. So if you're tuning your autoscaler, this is all hooked in already. Generally, the way when you want to start using these is when you have a known query pattern or a result set that you want to go serve back to your application. So that might be a real-time dashboard that's calculating store-level inventory. It might be vehicle telemetry data that's coming in, and you want to go identify outlier airbags or airbag deployment, something like that. Or it can even be something as simple as a rekeying. You can do an asynchronous secondary index with these. So if your application has two different query patterns, I need to go look up by email, I need to go look up by user ID, you can generate those patterns with this as well. And so we are continuing to invest in the SQL area. Just this week, we've launched several new capabilities in that SQL language. There's pipes, which are really handy for working with time series and telemetry and logging data. It's just a different variant of the SQL language. We have geospatial operators if you have to deal with mapping data or figuring out a lot of logistics. Companies are asking for this. Windowing functions, just additional time series analysis within the SQL language itself, and protocol buffer support. So you can start to do SQL on top of protocol buffer data. So if your application was built in protocol buffers, generally in a database, that protocol buffer is serialized. It's just kind of now a value in a key value store. But with this, you can start to get real-time insights and understand operationally what's happening in your application, even if it's just using protocol buffers. And so with some of that background of these features, back to you to say how you use this for that challenge of finding the orphaned rows.
Yeah, let's continue on our row cleanup odyssey. So how do we find those orphaned rows? Bigtable SQL makes it surprisingly elegant. We query the key column family with a temporal filter. So any access keys whose timestamp has passed is filtered out. Then the mapEmpty function returns true when nothing is left. In this case, every access key has expired. The row is safe for deletion. The challenge isn't writing this query. It's running it across the entire key space, tens of billions of rows across hundreds of petabytes, which brings us to the systematic scanning that I was referring to earlier. Our first approach was random prefix scanning. Each worker picks a random prefix, scan that range for orphaned rows, then picks another. Simple, stateless, zero coordination. The problem is that this is a classic coupon collector problem. With n prefixes, random sampling needs roughly n log n draws to hit everyone. And the tail is brutal. The last few % prefixes could take as long as the first 90. With the thousands of workers scanning randomly, we are looking at 1.6 years to guarantee the full key space coverage. The fix is to introduce a deterministic multiplicative permutation. We take the full space of the prefixes, multiply each index by a large prime, and mod the space size. This gives you a permutation that visits every prefix exactly once, in order that's spatially spread out so the consecutive workers aren't hammering the adjacent tablet servers. Every worker walks the same permutation, just starting from a different offset based on the hash of its hostname. Zero coordination, zero shared state, and the key space naturally partitions itself across the fleet. The result is we got roughly 17 times speed up. Instead of 1.6 years, we are looking at 35 days with much simpler code at the same time. So you might even think of row cleanup itself as a migration, just one that runs continuously instead of once. Finding the orphan rows, removing a deprecated column, backfilling a new field, they have all the same problem. Scan, filter, mutate at petabyte scale. We built a systematic scanning infra once, and now every migration we run rides on top of it. And this is exactly why we are excited about containerized materialized view. Instead of us scanning tens of billions of rows, looking for where the row is ready for deletion, Bigtable maintains this view incrementally. The scan disappears. The migration becomes a read of a pre-filtered index. It'll be a step change in how we operate in this system. Now let's move on to the fifth challenge, which is the storage cost. At roughly 170 petabytes, even every small per gigabyte savings are real money. The curve is the key insight. A row is read intensively right at ingestion, but the access decays exponentially. By day 7, most rows are essentially code. They are retained for compliance reasons. They're still decryptable if needed, but almost nobody is reading them. The vast majority of our hundreds of petabytes is sitting in that long tail. Paying SSD price for data that gets barely read is the wrong trade. So we are moving to Bigtable's tiered storage, a per table, age-based policy that automatically moves older cells to the infrequent access tier. Same API, no application code changes. Bigtable just routes the code reads to cheaper storage underneath. And for the very codest tier, the content at passkey expiry held only for legal or compliance reasons, we are looking at HDD-backed storage at roughly 5 times cheaper per gigabyte. And Chris will expand on the tiered storage.
Yeah, just to quickly double-click on what that tiered storage is, this is a fully managed way where you can do data lifecycle within Bigtable itself. You can set basically a time to live on your data. The data can remain hot in an SSD layer for more recent data, but then after a period of time, automatically move into more of a analytics price storage tier, and that really helps you balance the cost of storing all of this data along with getting the latency you need. And again, this is a unified, consistent API, so you can keep that data whether you need it for and access it the same way that you always have. So if you wanted to keep that data for training models, analytics, or just auditing capabilities, it makes it a really easy way to keep it within Bigtable and still make it accessible.
Yeah, and now let's move to the final challenge, which is application layer eventing. This is a system that we built, but we love to delete. Today, every Bigtable mutations on our application side makes a paired separate event that we emit ourselves. Those events flow into BigQuery and powers eventually consistent indices so that we can answer questions like who has access to what without scanning the Bigtable. It works, but it's a dual write. 2 system, 2 code paths, and the consistent burden lives in our application layer. If the Bigtable write succeeded, but the event emit failed, the index drifts. We've engineered around it, but it's code we maintain, not a guarantee that the platform gives us. What we really want is for the event to be moved to the storage layer. Bigtable change stream already captures every single mutation at the source. So if we pipe that into PubSub, then the Bigtable itself becomes the source of truth for change notifications. No dual writes, guaranteed delivery. And we'll get to rip off the whole layer of application code. And you might be noticed, this is the same across all 6 challenges. Every time we can push a guarantee down to the storage layer, our system gets simpler and safer. Chris is going to show you what's coming more for the PubSub with Bigtable.
Yeah, this application eventing and PubSub, for years, this has gone hand in hand with Bigtable. And so what we've started to do now is just make it even simpler to have these 2 products integrate. So PubSub had already had streaming ingestion, had already had a streaming subscription for BigQuery and cloud storage. But oftentimes, those analytic services did not address the needs of customers who wanted to build those faster, more responsive applications. And they wanted to move to more of this real-time data ingestion into an operational database. And in the past, that might have been complicated, but now with this new PubSub subscription that is currently in preview, you can have a PubSub message that directly, you basically go into the console, turn this on, and then it'll start to immediately write that data into a Bigtable table. And from there, you can put on a continuous materialized view or manipulate it however you want, so that data is ready in your for applications in that operational layer.
OK, now let me highlight the key takeaways. First, Bigtable's cell-level timestamps are much more powerful than many people realized. They enable our entire retention and access revocation model. Second, you want to push the security guarantees as deep as possible into your software stack. Cryptographic enforcements cannot be bypassed, but application-level echo could. Third, understanding your access pattern could unlock massive cost savings. The exponentially decaying reads paired with the infrequent access tier have cut our storage bill dramatically. And here it is. Claude does the inference. We compress and encrypt the data, store them in Bigtable. We use automatically expiring keys for access control, and build a systematic scan system for cleanup and migrations. Bigtable is the foundation. The scale, consistency, and cell-level timestamps makes this architecture possible. Thank you, and thank you to the Bigtable team. I'll hand over to Chris to talk about what's coming next for Bigtable.
Yeah, so we'll just leave you guys with what's coming up for Bigtable and some of the things that we're working on to evolve Bigtable for this new agentic era. So we have had customers for a long time. Bigtable can already give you single-digit, very predictable millisecond latency, but sometimes that's not enough, or sometimes you have hotspotting. And so this is why we have now introduced an in-memory cache or an in-memory tier within Bigtable. And that's going to give you sub-millisecond latency on subsequent reads. So what data comes in, once you read the data once, it'll go into this in-memory tier automatically. That will be consistent with the underlying layer, so you do not have to worry about cache invalidation or going over to some separate system or stale data. This is all essentially, you can go into the console, there's a checkbox, and then everything from here on out is managed. And so this really gives Bigtable a full end-to-end unified unified experience that's going to balance cost with the performance that you are looking for. So each tier, like if you can just imagine maybe like, we'll make up like a social network sort of scenario. I have a Taylor Swift or a celebrity row in my database, and everybody's going to go hit that. And so that can automatically move into that in-memory tier. You can get up to 125,000 QPS per node on that, and you're going to get that sub-millisecond response. But then you might have a row key for my data, and that gets pulled every here and there. No one really cares, but you could still want to serve that in under 2 milliseconds. That might be your SSD layer. But then you want to have all this data around for your analytics, for your machine learning training, or just to get back on an unexpected time, and you're willing to trade some latency there. Then you can have that move into that infrequently accessed tiered storage. And all of that, again, unified experience, unified API. You're essentially just flipping checkboxes or setting TTLs, and all of that is fully end-to-end integrated, so you're going to get the right cost for the latency that you want to get out of Bigtable. And so with that, if you want to get started with Bigtable, the best way to do it is with this free trial that we just introduced this week. So probably a lot of you in the room, you read that Bigtable research paper that came out 20 years ago, and maybe you thought it had a really cool architecture or a neat data model, but it kind of stayed academic. Now you actually have your ability to get your hands onto Bigtable. You can get started for free. There's no credit card to sign up. You can get 10 days of Bigtable. If you're actually using it, you can then extend up to 90 days. You get a full Bigtable node, which is enough to go start doing some basic benchmarking and get a feel for it. And you get 500 gigabytes of storage, because we're Bigtable. We want to give you the ability to even test out a pretty big table. Within this experience, you're also going to get this in-trial guide that will give you more insight into how do I actually work with these cell timestamps, how do I work with flexible schema. We'll give you the ability to load in some ready to play with data sets and some sample queries to get you started, as well as help you load in data from BigQuery or another tool. So if you can, go check out the trial. I think it's a great way to get started with Bigtable. And so with that, we really appreciate everyone coming out. Your feedback is really appreciated, so please fill that out. And thank you. We'll be around for questions over here if anyone has them.